The Gen 4 Coyote Engine Cover Adapters are specially designed to enhance the look of the Gen 3 Coyote engine. Designed in-house by Sanders Street Rods, the idea came from a customer looking to improve the look of his engine bay. Gen 4 Coyote Engine Cover Adapters are a quick plug-and-play solution by simply pushing them into the OEM grommets. The process starts by taking a 12-foot stick of 6061 aluminum and using the bandsaw to cut an oversized billet block with the dimensions of 1.5 inches by 3.5 inches by 1.3125 inches. The bandsaw uses a water and coolant mixture that provides cooling and lubrication to the blade throughout the cutting process. Each billet block cut on the bandsaw will go on to make 2 adapters. On a typical run, roughly 20 billet blocks are cut to produce 40 finished adapters. The billet blocks are then cleaned off and taken to the belt sander, where the edges are deburred to remove any sharp burrs caused by the bandsaw. After deburring, 2 blocks are placed in the Haas VF2 Vertical Machining Center, also known as the CNC mill. The blocks are then hit with a rubber mallet, seating them onto the parallels. The doors are then closed and the cycle start button is pressed. The milling process begins by grabbing the face mill and surfacing what will ultimately be the top of the adapter. This will provide a smooth surface finish by removing the rough texture from the bandsaw. This tool is only used on the top surface because the remaining sides will be finished in the coming operations. The face mill is then swapped out for a 1/2 inch 3-flute carbide flat end mill. It starts out by splitting the billet into what will be 2 of the 4 adapters. This tool will provide roughing and finishing operations on the 4 outer sides of the adapters. It now starts roughing the sides of the billet to form the curves of the adapters. During normal operation, a water coolant mixture, similar to what is used during the bandsaw cut, is consistently sprayed onto the operating portion of the machine. This keeps the tool and the workpiece cool and lubricated throughout the machining process. If coolant is not used for an extended period of time, it can cause excessive wear or damage to the tool. Next, the tool bores a hole with a helix. This motion is similar to a corkscrew. With this movement, it decreases wear opposed to plunging the tool straight down. It will also cut a bigger hole, allowing for improved chip removal. Chips are the metal fragments expelled by the cutting process. The purpose of the hole is to provide a mounting location for the rubber grommet. The rubber grommet is what the Gen 4 engine cover will be pressed into when mounted. Now you will see the flood coolant being sprayed. While this particular machine only has flood coolant, through tool coolant is also an extra option that can help with chip removal. For viewing pleasure, the coolant is toggled on and off throughout the rest of the video. Next, the 1/2 inch end mill is swapped for a key seat cutter. This is a milling tool where the cutting edge is larger than the shaft. This tool is used to finish the inner diameter of the bore, which provides an undercut, allowing for the grommet to be held in place. This is an instance where the coolant is not only used to cool and lubricate, but also used to evacuate chips to prevent excessive wear on the cutter. The rubber grommets are original equipment manufacturing that are suited for the Gen 3 Coyote engine. They are pressed into the adapter and held in place by a small, hook-like piece that grips on the portion that is currently being milled. This next tool is the final piece used in the first half of this operation. It is a 3/8 diameter carbide 45-degree chamfer mill. The purpose of this tool is to break any sharp edges that have accumulated by putting a small 45-degree chamfer on the perimeter. Most parts in the CNC process are chamfered, and it is typically the final tool path of the machining process. This gives the parts a finished look and feel. The parts are blown with compressed air to remove remaining chips and coolant before being removed from the machine. Now, all the machining for Operation 1 is complete. The parts are then flipped and preparations are made for Operation 2. The second operation begins with the blocks being placed in the vise and pushed against the work stop. The vise is tightened and the mallet is used to seat the parts on the parallels. The half-inch diameter 3-flute carbide end mill is used once again. This is used to rough away any excess material on this side. Substantially more material is shaved away, as this side contains the ball stud that seat onto the Gen 3 grommets. A tool's life cycle is dependent on the material and the aggressiveness of the cut being performed. This can vary depending on the amount of material needing to be removed. This current part requires less material removal, thus the tool has minimal wear and can make hundreds of parts without an issue. When the tool does wear, there is a slight adjustment that can be made within the machine's control to compensate for the fractionally smaller tool. This, generally, is only a couple thousandths of an inch. Here, the two adapters are finally separated and the final form starts taking shape. This tool is once again used for the roughing and finishing operations. During the roughing operations, a larger axial and smaller radial cut is used combined with a high feed rate to remove excess material quickly. This can leave an undesirable surface finish, which is then dealt with in a later operation. An axial cut is the length of the cutter being used, whereas a radial cut is the width of the cut. This style of machining utilizes the entire length of the tool opposed to just the end. This provides consistent wear along the flutes, which extends tool life and has a higher material removal rate. In this operation, the roughing toolpath leaves 5,000 stock, excess material, in both axial and radial directions, to then be removed by finishing passes. With better fixturing, more adapters could be done at one time. The current setup only allows for 2 billet blocks to be done at once. Fixturing is a generic term. In this case, it refers to a work holding device that can hold many parts at one time while utilizing one location point. Fixturing increases part density in the machine, allowing for longer run times, fewer tool changes, and increases uninterrupted machine runtime. The second tool in Stage 2 is a custom ground 3-flute carbide end mill. This tool was specifically designed for this part to machine the ball stud more efficiently. In the beginning stages of the prototyping, a tool similar to the key seat cutter was used. However, it was not as efficient and it provided a less desirable surface finish. A 1/4 inch 3-flute carbide bullnose end mill with a 60 thousandths corner radius is now swapped in. This tool is used to bore a relief hole on the bottom side of the grommet. This feature was added to allow for a thinner overall part. During operations, when coolant is being used, it is continuously filtered through the mill and pushed back through to be used once again. This machine contains a 55-gallon coolant sump located underneath the machine. There is a series of screens and filters that the coolant runs through to filter out any chips before entering back into the tank. Some coolant is lost through evaporation, and over time the coolant requires a refill. A maintenance schedule is followed and the coolant is flushed and replaced accordingly. Once again, the 3/8 chamfer mill is swapped in to finish off the part with a 45-degree chamfered edge. The finished Coyote Engine Cover Adapters are removed from the machine and inspected for quality assurance. They are then prepared for final assembly and packaging before being shipped out for delivery. Did you get the googly eyes?
Yeah.